I'd have to say I'm a little surprised to find myself here, because I think it's kind of rare to get a talk at Black Hat by promising to not attack anything. We are going to exploit something, although I use that term a little differently than we often do. We're going to exploit a resource that exists in a lot of organizations already, and that's a whole bunch of functional tests in order to find a bunch of security vulnerabilities. This second slide is not too exciting. I think the most exciting thing is going to be trying to watch Jacob and I dance back and forth as we switch between topics here. I'm going to give a little bit about our motivation for the talk and then make Jacob do the heavy lifting by actually describing the technique we're proposing, dynamic taint propagation. Now I'm going to get to kibitz and talk about sources of inaccuracy, places where the technique will not work, in an effort to try and maybe get a little bit more understanding about where it will work. Jacob will do some on integrating with the quality assurance organization, and then I'll go through about 30 years of history that the security community has of trying to use taint propagation in one form or another and boil it down to 5 or 6 slides, and then just a few parting thoughts. All right. The motivation, I'm going to use a couple of logical symbols to try and give some banners that I think a lot of security work happens under. And the first one I'm going to use is existential quantification. There exists is the way to read that when you see it in a logical formula. And if you use it in a sentence, you might say something like, there exists a vulnerability, again. And a lot of security people or people who do security testing are quite willing to stop here with existential quantification. The whole point of doing the security test is to prove that a problem exists, that something is wrong. And that's okay. A lot of people still need to hear that message, that there are security problems out there, and some of them are even in their code. We're interested in coming at this from a little bit of a different point of view, though. We're more interested in universal quantification for all. Like, for all bad things that might possibly happen to the program will be safe. That means we don't want to find the existence of one bug. We want to know about all bugs. Now, that's ambitious. In fact, it's pretty quickly provably impossible, but we aspire to it, and we think we can get much, much closer with a very, very different take on finding security vulnerabilities. All right, so if you're going to set out to find all of the bugs, and your organization looks something like this, you've got a big software development organization and a little itty-bitty security group, and I'd say that's actually pretty typical. What are you going to do? Well, obviously you'd like the security team to not be trying to do all of the work. Let's break down that software development organization a little bit, though. I'll break it roughly in half into programmers and testers. Now, we spend a lot of our time talking about what do you do for these programmers? How do you get them to write better code? And that's good, but let's not ignore the second half of that circle. And I'll say, this is not to scale exactly. Let me give you some, you might think you're going to get a fortified guy up here, and I'm not naive. I know that some of you at least are wondering, are you going to get your last yet another lecture on static analysis aimed at software developers? And the short answer is no. Today we want to talk about quality assurance, and we want to talk about, and the reason we don't want to talk about static analysis in the context of quality assurance, because using a good static analysis tool means knowing a lot about reading and writing code. And that's not a skill that's at the top of the quality assurance requirement list. The diagram that I showed earlier isn't quite to scale when I broke development and QA half and half. In fact, at Microsoft, right around 2000, there were more people working on quality assurance than there were working on actually writing code. That's interesting. That means you actually might have more spare cycles in the quality assurance organization than you do in the development organization. All right, so let's talk a little bit about doing quality assurance testing versus doing security testing. And we'll start by taking a look at the people doing the testing. People who do functional testing know the program, and they know the program really, really well. Security testers, generally speaking, know security really, really well, and they know a little bit about the program. How much do they know about the program they're testing? Generally speaking, they know enough to find at least one juicy vulnerability. The functional testers need high coverage, and they need high coverage because if the program goes out into the world and people who are the expected users of that software can't make it do what they want it to do, that'll come back to the functional testing folks. Security testers particularly who live under there exists existential quantification, need to find one vulnerability, and then they've done their job. How many pen test reports do you come back and say, no, that's cool, the software is good? It doesn't happen. And the reason it doesn't happen is because there's no good science for them to explain what it is that they tested. So the only way to know that they did their job is when they find a vulnerability. Okay, functional testers have a lot of time and resources. Now, if you ask them that, that's not the story that you're going to hear. So I'll add comparatively. In comparison to people who are doing security testing, who often show up a little bit late to the game, like, oh, hey, we already built this thing and released it, and maybe you could do something with security testing on it now? Ever heard that before? They also often get asked to leave a little early, not just from DEF CON. They get asked to leave early because there's a fixed budget for doing security testing, frequently. All right, so now that we've talked about the people who are involved, let's talk a little bit about how the test process itself happens in functional testing and then in security testing. So typical software testing looks a little bit like this. You've got a program under test. My background is in hardware design, so when I like to simplify these things, they start looking like circuits. You take your program under test and you apply some inputs to it, and they're happy inputs. In other words, they're inputs that are described in the specification for the program. And then you look at what kind of outputs you get. Happy inputs, happy outputs, everything's cool. You do this a lot with a lot of happy inputs, and sooner or later, you find that happy input leads to unhappy output. And that's a bug. Fair enough? Okay, now we'll talk about typical security testing. Here, you apply malicious input, bad stuff, the worst stuff you can think about. Happy inputs? Okay, maybe those malicious inputs weren't quite as malicious as we thought they were. Okay, so we'll just do this a bunch, right? We'll apply a bunch of malicious inputs, and sooner or later, that program dies. Aha! That's a good deal. I've got a clear indication of a vulnerability. I did something unexpected, and I got that program to just fall over. It's also good because I've got a test case to prove it. So if I need to file a bug or describe what's wrong, I can say, provide this input to the program. Yeah, it's not what you thought people were going to be providing to the program, and I can make that program die in some way that I can exploit. Okay, so typically that approach goes under input fault injection, or is called input fault injection. Input fault injection is good for the reasons that I just discussed. It's also got some downsides, though. Bad input typically derails the normal flow of a program. And that means that you can't mutate a set of functional tests and expect to retain good coverage. Think about this very simple example here. Think about a website with a 3-page flow where you add something to a shopping cart, then you go to the checkout and enter your shipping information, and then finally you enter some payment information. Now at each of these stages, the program accepts input from the outside world. Imagine we've got a bug in the part of the program where we enter a credit card. Well, if you've been supplying malicious input all along, you put the program in error states, you end up not testing that enter credit card field nearly as much as you end up testing the states before it. This gets worse and worse and worse. If you think about what you need in order to achieve good functional test coverage for a flow like this, you need a multiple of that in order to achieve good security testing under a fault injection model. That's a bad deal if security testers are constrained to fewer resources than the functional testing folks are constrained to. Basically, it means we're likely to get bad test coverage, and that means we're likely to miss vulnerabilities. We published data on this actually at DEF CON last year and showed a bunch of black box tools and the generally dismal test coverage that they achieve. Okay, so I'm going to turn this over to Jacob in just a minute, but let me try and summarize the problem this way. QA organizations have good test coverage and they've got good time and resources. Those are generally speaking two things that the security team lacks. The security team, on the other hand, has a clue about security, and that's generally speaking something that the QA organization lacks. So what we're looking to do is to try and combine the strengths of these two organizations and find a way to involve QA in the security process. Our biases when we do that are to favor false negatives over false positives, because we don't think we can get a quality assurance organization to go through reams and reams of findings and interpret them. So when we tell them there's a vulnerability, we better be right most of the time. That means we better expect that the security team isn't going to abandon us and turn all of their work over to the quality assurance team. What we just want to do is come up with much cleaner code coming out of the development process. We need to find a way to leverage stuff that QA is already doing, because they're not going to go become security zealots. That means we've got to find a way to leverage the testing they're already doing and transform those tests into security tests. All right, Jacob, have I made a big enough mess? Think you can clean this up?
I don't know, but I'm feeling motivated. Okay, so I think Brian set the stage well for what we're going to talk about. I'm going to dive into the technology that we want to apply and a little bit about our specific implementation. So as Brian said, what we want to do is find more security vulnerabilities, and we want to leverage the existing resources, both in terms of people and functional tests in the QA organization. What that really comes down to in our case is tracking input through the program. So a lot of security vulnerabilities come down to what an attacker can supply, that malicious input that we use in fault injection, and how it can be misused in the program. So an example, very simple vulnerability that you might hope to find with dynamic taint propagation is this SQL injection vulnerability. So up at the top, we read a request parameter, set it into this user string, we concatenate it into a dynamic query, and we execute it. Pretty straightforward. So in order to find that with taint propagation, what do you need to do? So you need to identify the sources of input, in this case, getting the request parameter. You need to be able to propagate that knowledge about input as the data move through the program. And you need to be able to identify points where it's misused or it reaches a sensitive API like the SQL query being executed in this case. So this is a general approach, and you can apply it to various languages. We've built implementations for Java and .NET already. I expect to see others in the related work section. Brian will talk a little bit about similar techniques that have been applied to other languages. Today, I'm just going to talk about Java for a little bit of simplification. So what do you need to do first? You need the ability to track this concept of taint. So you identify places where taint enters the program, but how do you store that knowledge? So in Java, we care most about strings. Most exploits against vulnerabilities in Java programs that have to do with malicious input at least come by way of string input. So we're going to modify the Java string class to include a taint marker, so the ability to tell whether a given string is tainted. We also care about, as I said, being able to propagate that taint. So when you concatenate two strings, or you take one string and then modify it somehow, how do you carry on the knowledge that the original string was controlled by an attacker? So we need to modify string builder, string buffer classes to propagate taint in the appropriate way. And so as you would expect, two untainted strings being combined leads to an untainted string. Any tainted input being included in another string leads to a tainted string, and so on. So I mentioned being able to identify sources of input. So now we have this foundation, this infrastructure for tracking taint, but where does it enter the program? So we need to know about APIs that introduce user input. This might be things like reading request parameters. This might be data coming out of the database for things like persistent cross-site scripting. This might be the file system. This might be the environment. Anything you can imagine caring about from a user input standpoint, or what an attacker might be able to control. We also care about what the sensitive APIs that data shouldn't ever reach are. So executing SQL queries, being written back out to the web, going to the file system, path manipulation, all the old stuff. So here's our original SQL injection vulnerability. And this is certainly an abstraction. So in the bytecode, at the bytecode level, A, the original code is a little more complex, and B, what we do to modify it is a little more complex. But at a high level, this is what we're talking about. We introduce a call to describe or set a property of that string that it's tainted when it's read from an untrusted source. We add logic to propagate that information when it moved from one string to another. And we add logic to check whether a tainted string is being misused when we call one of these sensitive APIs. So what kind of results would you expect to see from such a tool? So everybody's seen security dashboards before. This one isn't any different. It gives you an overview of the kinds of vulnerabilities it might have found. One of the interesting things that it lets us do, this technique lets us do, is start to talk about coverage. And so this terminology is used in the QA organization already. But in this case, we can apply the concept of security coverage. So you can see as we identify all these sources and sinks, we're talking about what are the interesting parts of the program from a security standpoint? What do we think that you need to exercise as part of your testing? And now that we've identified all those points, we can tell you, did you test them or not? It doesn't have any implication on whether you tested them well, but if you didn't test them at all, then you're guaranteed not to have tested them well. So when it comes down to it, what we're really looking for are vulnerabilities. And in this case, we've got a SQL injection vulnerability, the one we talked about earlier. And when you dive into it, the interesting thing about this approach is you get a little more detail than you would with typical fault injection or any kind of black box approach. Because you've instrumented the program itself, changed its source code effectively, and we'll talk a little bit about that technique in a minute, you get a lot more information. You get information about where the input entered the program, and you get information about where the vulnerability occurred or where that input reached a sensitive sink. Not just information about what the sink is, but the source file, line number, all the details to go in a bug report or go back to development to get the problem corrected. So typical black box results look something like this. You get a URL, maybe the input that went into the URL. So here's the request, here's the malicious input that I provided, and I saw a stack trace come back, or I saw some indication that led my oracle to believe that there was a vulnerability. With this approach, you get a lot more detail. As I said, you get to dive into the source file, you get a stack trace for how the program executed, what execution path led to the sink you're interested in, and you get information about the vulnerable data itself. So here's the query that I think suffered a SQL injection. Here's the JavaScript being written back out to the dynamic HTML. So how do we go about doing this? You could take various approaches. You could just take your source code and rewrite it to perform taint propagation. That's really what we're talking about. Now, in order for that to be generally applicable and more accessible, you've got to automate that some way. You can't have a one-off for every program you write. So we're talking about modifying the program after it's written, so taking the war file, jar files, and rewriting the bytecode in some way to add this logic that we've discussed, identifying sources, propagating taint, and looking for when it reaches sinks. There are two components of this. So there are the core classes that you need to modify. In the case of Java, the JRE classes, string, string builder, and so on. And that's kind of a one-shot deal. You need to modify the platform that you're going to run your program in, but you don't need to do that every time. So our approach performs this once statically. You modify rt.jar, make the changes we're interested in, and use that when you're testing your program. Now, the second piece is you need to modify your program classes to identify things like sources and sinks as well. You could use a similar kind of static approach to that and modify it on disk. We call that compile time modification. So you change your war file, you deploy that, and then test it. The preferable approach, I think, the lower impact approach, is to modify the class loader, typically in your application server. So when you deploy a new application on the application server that's designed for this sort of testing, you get instrumentation for free. So as the program is loaded, you modify its classes as they're being loaded into memory, and then what you get is effectively the changes that we saw in the SQL injection example. In our case, the technology we chose to apply to this is called aspect-oriented programming. And the idea behind, the motivation behind aspect-oriented programming is taking peripheral and cross-cutting concerns, so not core business logic, but things that need to apply throughout a program or across multiple programs, and extracting it from the original program source and bringing those two together at some point after the business logic is written. It's great for security, it's great for logging. People have been using it for quite a while. There's some open source frameworks. We use AspectJ, AspectDNG. These allow us to specify those sources and sinks, the information we care about, externally and apply it to any program written in the given language. You could very well build such an instrumentation approach, even if you wanted to modify bytecode after the fact. So you could do this without one of these frameworks. You could do it without ever talking about aspect-oriented programming. You'd probably want a library like bcell or ASM to do your bytecode rewriting, because that's kind of a pain. But in general, it's not too bad. Here's an example of what one of those aspects looks like for execute query in Java. So it allows us to specify that what we're looking for is a call to statement execute query with a string argument. And this lets us, again, externalize that specification of what we're interested in. And this is kind of equivalent to a lot of security tools having rules. So we talk about these things as being rules, which let us describe what it is we're looking for. One of the big considerations when you're talking about an instrumentation approach is, so you have this long list of things you want to look at, execute query being one example. Do you instrument outside of a call to one of those APIs, or do you instrument just inside the definition? The advantage of looking inside the function, or placing that instrumentation inside the function body, is you have lower instrumentation cost. There's only one call, there's only one implementation of execute query in the context your program is running in at a given time. So that's one instrumentation point, as opposed to there might be many, many calls to that. The downside is you don't get as much information when you want to report a vulnerability, because you have to somehow go back and distinguish different call sites for that instance of execute query. You can certainly do that looking at the stack trace, but it introduces more runtime overhead and potentially makes reporting harder. So for our initial approach, we've instrumented around function calls. So every time you call execute query in your program, we're going to add the necessary checks to tell whether the argument is tainted. I think in the future we'll probably be more intelligent about this and do some sort of hybrid approach, where sometimes we instrument the body of the function, sometimes we instrument around calls, depending on the way we expect to see it used. Another, diving a little deeper, something I oversimplified before, I suppose, is that you don't really want taint to be a binary property. So you can imagine a string either being tainted or untainted, and that's kind of the way I've described the approach up until now. But it's actually interesting to have more dimensions of taint. So to start to be able to distinguish between taint that comes from the web or from the database or from the file system. And this is useful both in terms of not reporting vulnerabilities in cases where it's not very relevant. So cross-site scripting coming from the file system. It's not really an attack vector we think about typically for cross-site scripting. But it's also useful in changing the priority. And in particular, when you're talking to an audience like the QA organization who's not used to triaging security results, they're not going to become security experts. It's really useful to be able to put the things you think are most important at the top of the list and allow them to draw a line somewhere and say, we're not going to look at things below here from a priority standpoint. So the implementation I described before is actually a little different. We in fact modify the string to include not only a taint marker, but also some information about the source. Where did that taint come from? So now at the sink, when you check for taint, you can also check for where it came from and pass that information along to the reporting interface. Rules, or aspects, as I talked about them so far, are critical. If you miss one component of one of those data flow paths that you're interested in, then you're not going to find the vulnerability. This isn't news to anybody. Thinking about the right set of coverage for the third-party libraries, the frameworks, the APIs that you use is critical in making sure one of these tools is going to do a good job. Luckily, people have been thinking about what these sets of APIs are from back in the days of RATS and ITS4 and the very early static analysis tools that basically just gave you a list of APIs. So some of this knowledge exists, and you can and should leverage it if you develop such a tool. And that's the end of my slide, so I'm going to turn it back over to Brian. I wasn't expecting that one. I thought there was one more.
Oh, come on, Jake. You're going to roll. Just keep going. Okay. Okay, so did it all sound great? Does it all sound wonderful? Anybody got any, any qualms at this point? I've got a whole bunch, but I just thought I might ask you for yours first. No, you want to see mine first, and then you can tell me yours. Okay, that's fair enough. Okay, so I mentioned two types of errors before. False positives are erroneous bug reports, and they're painful for the tool user because the tool user's got to make a decision now about, does the tool tell me the right thing? Can I put this in the bug database? Do I have to validate it somehow? What do I do? And false negatives, which are bugs that the tool doesn't report. Now, in the grand scheme of things, given my introduction about universal quantification, we're actually much more worried about missing bugs. But when we're talking to the QA organization, we'll sacrifice. When we have to choose between a false negative and a false positive, we'll choose to not report anything, take a false negative, because we want to keep life simple for the quality assurance organization. Okay, so let's talk about where false positives come from. Unrecognized input validation. So here's the example that Jacob showed earlier, but I've added 3 lines in the middle. You get the request or the data from the user just as before, but now you run it through a function called isAlphaOnly. And if alpha-only returns false, then we bail. That means there's really no opportunity for an attacker to deliver a malicious payload to this execute query. Of course, there's still a path from that input all the way through to the execute query, so if we don't take any extra steps, we will report this as a potential vulnerability, even though it isn't one, and that's why it's a false positive. More generally speaking, what we're talking about are impossible control flow paths, paths that regular data can take, but that malicious data could never take. And the solution to that problem is to introduce cleanse rules. In other words, we will augment functions so that we will remove taint under certain circumstances from strings. We remove taint, for instance, when someone compares against a regular expression or when they compare against a static string. All right, so our second weapon against false positives is bug verification. And that basically is training wheels to get people who are used to doing functional testing into the realm of security. We can show them, when we give them an error report, which inputs to attack, and we can also suggest attack data to them. That means that they can come back to the program and they can say, oh, okay, well, you know, maybe I ought to see if I can pop up an alert dialog here when it tells me about a cross-site scripting error. Oh, look, and they gave me the string to enter and the parameter to enter it on. And then we can do one more thing. We can actually monitor in the program what happens when they try to do that. And so when they really trigger a vulnerability, we can give them a gold star. That's important if you're talking to somebody in the QA organization and you have, say, a SQL injection vulnerability that's only going to be exploitable via a blind SQL injection attack. Most people who are doing quality assurance testing, they're not going to get the whole blind attack notion. But if you come back and say, gold star, you found a bug, file this one, because we were monitoring that SQL call site, then we're in good shape. Okay, let's talk just a little bit about false negatives. False negatives come from a few sources. The one I'm going to spend most of my time in the next few minutes talking about are when taint goes places that we can't follow. But there are a few other things that can go wrong too. People can write bad cleanse rules, or they might just have bad functional test coverage. Okay, so let's go back and talk a little bit about taint going where we can't follow it. So string decomposition is one example. Here I've got a little bit of code. All it does is it takes a string input named tainted, declares a string buffer, and then one character at a time pulls out of tainted, puts it into the string buffer, and then at the very end returns a string named untainted. What happened here? Well, we decomposed the tainted string into individual characters. Individual characters in Java aren't objects, and that means we have nothing to attach taint to. That means we'll lose track of taint going through code like this. Insufficient input validation is another problem. Here, this is exactly the same piece of code from before. But imagine we write a cleanse rule that says, if the string goes through alpha only, when it comes out, we're cool. Except, what if somebody doesn't implement alpha only correctly? Well, then we'll be removing taint from the string, even when the string should be tainted. And then, of course, there's sort of this degenerate case, which is we're only going to examine paths that are actually executed through the code for vulnerabilities. We aren't going to add additional paths. And that means that if you don't thoroughly execute the code, then we won't find the vulnerabilities. This, though, is a violation of our fundamental premise that the QA organization has more resources than the security organization and will create tests that exercise a wide number of paths through the program. Jacob, back to you for integrating with QA. Yeah, I got off easy on that one.
I would really like to say at this point that I don't know how I got stuck talking about process, because I know it's basically everyone's least favorite topic. I got stuck talking about it because I actually think it's important. I won't belabor it too much, but I do think it's kind of critical. So in practice, we're talking about this new technique, this new approach that's going to be used by some combination of the security team and the quality assurance team. And you can imagine this is kind of a spectrum. You could imagine a world where everything is performed by QA, but that probably requires more security expertise being developed there than we expect to see in practice. In fact, I want to break up what we're advocating into 4 steps. So there's the instrumenting the program. And this might mean setting up your platform, changing your app server, that sort of thing. It might mean doing compile time instrumentation. There's performing your functional tests. And this is the only one that really, there's only one right home for it, which is the quality assurance folks. We're not going to get security testers in doing functional testing, no reason to. There's triage and verification. So you run these functional tests, you get a big list of results out the other end. What do you do with those? You need to decide if they're real, if they're not real. And then you need to take some remediation steps. So report this back to the development organization and make sure it gets fixed. Like I said, everyone except the functional testing could be and is likely to be a combination of quality assurance and security. And depending on the organization and the capabilities of these organizations in each, you could see that shifting more left or more right. So on the instrumentation side, either QA or security could do this. The key considerations are, do you know enough about the program to decide whether your instrumentation strategy is going to do a good job? Are you covering the kinds of APIs, the kinds of business logic that your program uses? From the security standpoint, whether you've covered those APIs or not, you need to know whether you're doing the right thing with them. Are you treating them correctly? So there's a little bit of evaluation from both ends here. If you've got a good tool coming from the outside, then you could imagine just leaving this up to wherever you got the tool from. If your security team built the tool, then the QA organization can assume that it's going to do a good job on their program. It could be risky if they're missing something about what the program does, but in general, not a bad tactic. So we expect to see this mostly fall in the land of quality assurance. Functional testing. So QA is going to do this one for sure. They're already trying to maximize coverage because they want their functional tests to do a good job covering the application. Now, there may be a new metric that we're going to introduce to the story here, which is security coverage that we talked about before. So do those functional tests do a good job of exercising the security relevant APIs? And you might imagine a program that has 97% functional test coverage, but only 70% security test coverage, because that little bit that they missed are actually very relevant from a security standpoint. So you might see a new feedback loop being introduced here, a new metric being used, but more or less it's the status quo still. The good news is security knowledge isn't so necessary, and obviously the point I just made seems a little contradictory to that, but you don't need to understand why those APIs are relevant or how to best exercise them in terms of the data that eventually make it to the APIs. What you care about is, did I run that line of code? And that's what the QA organization is already doing and is pretty skilled at. So triage and verification. This is kind of where the rubber meets the road. You need some security knowledge to evaluate the set of results coming out of the tool. This approach, like any other tool or any other approach, isn't going to produce 100% true positives. There's going to be some weeding out of the things that aren't interesting, aren't relevant, don't apply in this context. And the security team is likely going to have to play a role in that. In order to do a good job evaluating one of these issues, obviously you need to understand a little bit about the program, and this is back to what Brian said earlier, that the security team probably knows something about the program, but they may not know enough. So in terms of doing a deep analysis like this, they may actually need to rely on the quality assurance organization to tell them some about the program or go back to development. But security is really the key. Now, there are things we feel you can do to bring quality assurance not make them into security experts, but bring them into the fold a little bit here. So you can handhold them in developing some exploits. How many web applications have incredibly stupid cross-site scripting in them? A lot of the ones I look at. And developing an exploit for one of those isn't that hard. I can write you a step-by-step set of instructions, and you might get half of them. I don't know. The goal, again, just like when we say we're not going to, or we're going to favor false negatives over false positives, isn't to get all the bugs here. It's to get as many as we can using this resource that we've got, bringing another group into the process. And that's an important part of, you can develop exploits for some simple vulnerabilities, but maybe not the harder ones. Different kinds of bugs, cross-site scripting was one good example, are easier to evaluate whether they're true or not, and to develop test cases for. So have the quality assurance organization target things you think they're going to be most capable of, and do some targeted training, specific training around those areas. Again, don't try to turn them into security experts, but bring them up a little bit in certain areas so that they can start to contribute, and leave the hard stuff to the security guys. So reporting bugs. You can imagine in an organization where security is doing all of the triage, they're doing all of the bug reporting too, because that's after the test is conducted, everything is handed off to the security folks. That may be a challenge for them because they may not know the bug reporting conventions, they may not know for a given part of the application where does that bug go. So there could be some interplay with quality still. If you've got quality assurance doing some of the triage, then it definitely makes sense for them to carry that on through to remediation, because they're already doing that with functional bugs that they find. The last piece, sorry, I almost missed a bullet, is remediation advice. So when you file a bug for security, you could assume, okay, the devs are going to know what to do with it. Not so much these days. You need to give them some advice, and obviously there's training needed on that end too, but it's good for the bug to say, here's what we think you ought to do about it. And that may require some input from the security guys. That was a short section. I promise not too much on process.
Okay, I mentioned earlier we've got at least 30 years of using Taint to find vulnerabilities. And so obviously I'm not going to cover everybody who's done that. I'm just going to talk about some of my favorites. Perl, some other folks who've done Taint propagation for Java, Constraint Propagation, which is more refined than just Taint propagation for C, and then some fine-grained Taint propagation approaches. Let me start out with this one. What's this Perl script do? I guess I should say Perl is probably the most widely deployed Taint propagation system out there. I don't know if it's the most widely used because I don't know how many people actually go and turn on this T flag. But what do you guys think happens if you run this Perl script? So all you do is you take a command line argument and you call system, and you've got this T flag at the top. Hey Jacob, we got a decent amount of time here, right? We can just sit in silence until somebody says something, right? Errors. It gives an error. What's the error? What error did you get out of this? Man.
He's patient.
Taint propagation. Chris. Come on. What's it say to you?
Who uses Perl? Tainted data used in a sink.
Tainted data used in a sink, exactly. But it's probably not the tainted data that you think it is, right? Obviously, if this is a setuid root script and you run this, then you're allowing whoever runs the command line to execute any command that they want. Maybe that seems like a bad deal. But maybe you don't entirely get at first blush all of the ways you could manipulate this line. The very first thing Perl will say to you is you've got an insecure environment. Because the input to the program isn't just coming from the command line, it's also coming from the environment that the process inherits from the person who runs it. So they can set any path they want, and then that command could mean anything they want it to mean. Okay, we can fix that by just setting the path to, I don't know, b/bin. All right, that's good. Now supposedly we should only be able to execute things out of /bin. Perl will give you the complaint that no doubt most of you were thinking of, and that is an insecure dependency while running with the -T switch. In other words, you're executing something you took directly from the command line. Now, Perl is set up much the same way we are to remove taint under certain circumstances, specifically when you compare a string against a regular expression. There's no guarantee in Perl that you compare it against the proper regular expression, but you get some way to not receive these tainted error messages all the time. Perl is set up as with its taint mode as a defensive mechanism, not as a bug-finding mechanism. That means that the error messages that you get out of it aren't really very useful for debugging, but at least they will stop bad things from happening when those bugs get into production. You hope. All right. A brief stop at taint propagation for Java. This is taken from a paper from Haldar Chandra in France, from UC Irvine, from ACSAC 05, and the paper that gets distributed with the conference materials actually has the links to all the PDFs for these, so don't try and scribble out the notes if you're just going to pick up the handouts later. Their system's very similar to ours in that they taint Java string objects. It's dissimilar in that they're interested in active protection, much the same way Perl is, as opposed to bug detection. They have the notion of taint flags, but basically no implementation. They've got the notion that maybe you'd like to make different security decisions based on where data comes from, but no real way to follow through on that. Next, I want to talk about a favorite paper of mine from the last few years, and that is one by Larson and Austin from University of Michigan at Usenix 03. And here we're not just going to propagate taint markers, we're going to propagate constraint sets. And that means basically at the same time that the program is executing in a concrete fashion, we're going to execute the program side by side in a symbolic fashion. And the idea is we're going to spot bugs where input is under-constrained. They reported multiple bugs in OpenSSH with this stuff and got a nice splash out of it in 03. So I'll give you a little bit of an example here based on a few lines of C code. So declare a variable x and an array of size 5, and then read data into that variable x. If x is greater than 4, then die, then manipulate x a little bit, increment it here, and then use it to index the array. Safe? Unsafe? Well, of course it's unsafe because it's an example of showing a bug here. But you might have a concrete execution that it's an expected case where you read in a value of 2 and then you compare that against 4, and of course it's less than 4, so you get to keep executing. Then you increment it, x becomes 3, and then you index into the array with it, and that's cool. Right? 3 is within bounds of the array. So how can you find a bug using this concrete execution? And the idea is to do a symbolic execution alongside it. That symbolic execution looks like this. When you first read in the value, x is greater than or equal to 0, and it's less than infinity. Actually, we could bound it a little more tightly because we know that x is an unsigned integer. So we really know that it's less than a 32-bit quantity, but fine, we'll just call that infinite. Then we compare x against 4. Now, if we successfully, well, if we don't die on that line, we know that the value of x is between 0 and 4 inclusive. Then increment x. Now we know x is between 0 and 5 inclusive. Then, when we index into the array, we get an error. We get an error because x might be 5. It might be trying to write 1 past the end of the array. So that's how we use the concrete execution to get a symbolic execution at the same time along the same control flow path and find bugs. All right, now I'm going to talk a little bit about fine-grained taint propagation. This paper was at Usenix a few years ago. Zhu, Bakhtar, Sektar talk about keeping explicit taint state for every single byte in the program. When I say fine-grained, I mean not keeping track of taint at an object level, but keeping track of it at an individual byte level. That requires a really, really big taint map. But they have a series of clever optimizations, including some static analysis tricks and a whole lot of dynamic analysis tricks that allow them to basically make the performance overhead of that taint tracking bearable a lot of the time. Basically, their technique looks like this. You've got the address space for the whole program. You cordon off a quarter of that address space for the taint map. Now, whenever you do something like read data into the program, say you read into that memory region towards the top, you set in the taint map the fact that those bytes are controlled from the outside. And if you then say copy that tainted memory over somewhere, then you update your taint map in order to keep track of exactly what in the program is tainted. Then when you get to a potentially dangerous operation, you can ask, are you operating on dangerous bytes? This technique is very general. You can detect buffer overflow attacks, format string attacks, all manner of injection attacks using the same technique. What's even better is if you've got an interpreter that's written in C, you can run the interpreter under this system, and that means that you can, say, find vulnerabilities in PHP programs using exactly the same technique. That's a good segue into talking just a little bit about PHP. PHP and a lot of interpreted languages make it easier to do fine-grained taint analysis, even if you're not going to go down all the way to keeping a fine-grained taint map, because all user manipulatable data in the interpreter has a native data structure that represents it, and much the same way that we modified the string class, you can modify the PHP interpreter object in order to carry that taint around for you. So you can actually augment the interpreter to propagate the taint. You get a much smaller performance penalty for this, generally speaking, as long as you're not manipulating reams and reams of tainted data. Core grasp, which, let's see, where did core grasp come from? I think it was at a Black Hat Las Vegas presentation last year, does exactly this. We'd like to see eventually this built into the PHP interpreter the same way taint mode is built into the Perl interpreter. Did you really think you were going to get away without a static analysis slide? No, come on. So you can do taint propagation with static analysis too. The advantage to doing so is that you can simulate execution of all paths. So we're no longer limited to this problem of having to actually stimulate the program to explore paths. We can just look at all of them in a reasonable amount of time. The disadvantage is static analysis is necessarily less precise than a concrete execution of the program. And the static analysis tool doesn't know which paths are likely and which are unlikely. So there may in fact be a set of paths you are much, much more concerned about, say those bringing data from the network, than the paths that are bringing data from the file system. And by default, the static analysis tool doesn't know the difference between those two. You have to tell it. All right, I'll finish off with just a few thoughts. We see security coming to quality assurance groups the same way security is moving into development organizations. It's not going to happen overnight, but security is going to make its way into quality assurance. What we can learn from our experience bringing security into software development organizations are, well, threefold. First of all, we've got to target what QA does well. The less kind way of saying that is that we can't take tools meant for security people and expect that quality assurance people are going to be able to do just as good a job of manipulating them. It's not going to work that way. Training is good. We're never going to get away without doing some training for QA organizations on security, but we can never expect to turn quality assurance into the security organization. We've got to find ways to leverage their inherent strengths. Okay, Jacob, now we get to stand up here together and answer any questions anybody might have. That's easy so far.
Do you have a tool set developed for doing this on .NET?
So the question was, do we have a tool set for doing this on .NET? And yes, we've developed implementations for Java and .NET so far, based on very much the same approach.
And, you know, we didn't present any of the .NET stuff because it really pretty well looks like a clone of the Java stuff with a lot of the names changed. You know, manipulating the MSIL is different than manipulating Java bytecode, but not it's not interesting in any way that it's good for an hour-long talk.
Okay, so what I meant is this publicly available, what you've done for .NET?
Yeah, so we make tools that we try to sell. The idea of today's talk actually is that this stuff is pretty easy to build. So it may not be easy to build well, and it may not be easy to deploy effectively, but a long weekend and some good libraries, and you could go build something that would do this yourself. In Java and .NET. If you want to go do it for C, it might get a little harder. Come on, a couple more at least.
Have you guys looked at any sort of way of specifically formalizing the constraints, like prior to application development? Almost like you want to implement, like a constraint is like a runtime requirement, right? Like you look into that, inserting that into requirements into your interface or software development.
Okay, so the question is, you've got some constraints on what the program is supposed to do. For the most part, people don't write those down these days, right? And so a lot of the security problem comes down to trying to reverse engineer what is the program supposed to do. If I can define what inbounds is and what out of bounds is, security becomes a lot easier, right? So I'll tell you, I haven't seen good automated ways to do that, although what you see a lot of tools like this doing, in a way, we are hypothesizing a set of requirements to the quality assurance organization.
Microsoft does a little bit of this in their system header files. So they'll put constraints around, this integer bounds this buffer or specifies the length of this buffer, and then you can do some automated testing or enforcement around that. I expect to see more of this coming in the form of notation of some sort on the source, but I think it's back to, as Brian said, you've got to come up with the constraints before you can worry about specifying or enforcing them.
When you talk about Taint, you're talking about a framework, not specifically tools, right?
So when we talk about taint, we're actually just talking about a value that is externally controlled, or that an attacker could presumably control. So you could replace taint with untrusted or potentially malicious.
So it's just the terminology that you're using here.
Yes, absolutely.
Have you been able to integrate this into the extreme programming paradigm and unit testing?
So the question was, have we been able to integrate this into extreme programming and unit testing? Haven't thought a lot about it yet.
I'll tell you the nice thing about any technique, though, that's working inside the code as opposed to trying to treat it as a black box, is it's going to be much more amenable to more different types of programming. So we talked about web and the kind of web examples here, but it really doesn't matter that we're talking about web applications. We could be talking about any kind of application here, which means that the taint propagation approach would work just as well under a unit test, although it's not something that we've done a lot of exploration of.
How do you augment the class order to change your runtime with your
So the question is, how do you augment the class loader in order to get all of this good stuff happening when the program runs? So if you can't augment the class loader, you just manipulate the bits on disk for all the classes. But let's say you want to do it at runtime. So as of Java 1.5, there's actually a command line hook that says, I'm going to specify a class name here, and I'm going to run before the class loader runs. Every time you want to load up a new class, call me first. In older versions of Java, you got to get a little bit more tricky about this. You've got to declare yourself to be the boot class loader, and then essentially you have to infect any class loader that gets derived from that boot class loader. So in older versions of Java, it gets a little bit tricky. In the new ones, it's pretty straightforward and decently documented.
All right, I think we'll call it then. Thanks, everybody.